Hello everyone, welcome to my presentation. Today I will present the paper, What Can Neural Network Reason About? This paper is published in ICLR 2020. This work examines the reasoning capability of neural networks, and they propose a theoretical framework to analyze their performance. Okay. Let's begin by defining what is reasoning. So reasoning is a process of deriving conclusions or making decisions based on given information or rules. For neural networks, neural network reasoning means learning to perform such the tasks using the data-driven representations. So example include like determining the shortest path in a graph, answering questions about some mathematical problems. So here the question is, how well can neural networks mimic or replicate this reasoning process? We start by identifying the challenges in understanding the reasoning abilities. So neural networks have demonstrated empirical success in various reasoning tasks, like the example like the visual question answering, some physics questions, computer science popular problem like shortest path problems. So, however, there is a problem. While neural networks perform well on some tasks, they fail on others. For instance, graph neural network often outperform MLPs in relational tasks, but we don't fully understand why this is the case. And this gap encourages the theoretical understandings to create some theoretical understandings about the reasoning. Okay. Next, let's consider the importance of the neural network structure. So neural networks with some specific structure, like previously said, graph neural networks, it always outperforms more genetic architectures like MLP, especially in relational reasoning tasks. So this observation raises a key question. So why do graph neural networks success, but MLP fail? What makes graph neural networks more suitable for tasks like shortest path or relational comparison? So that's why this is another reason that a formal framework is needed to quantify this alignment between the task reasoning and the network design. In general, this paper wants to answer the following question. What tasks can a neural network learn to reason about? In other words, how well a reasoning algorithm aligns with the computation of the computation graph of the neural network. So to address this paper proposed a theoretical framework, algorithm alignment. This is a framework that explains why some networks generalize better than others based on how their computational structure align with the reasoning tasks. In addition, this framework also helps to identify the limitations of current neural network structure, and it will provide a guidance to design a better model. So next, let's define some, before moving to the key contribution, here are some preliminaries. So a reasoning task often involves a set of objects. Each object can be represented as a feature vector, xs. So for instance, in viral tasks, these each object can be the object, the xs can be the object attributes. Then the task can be formulated as follows. Given a set of universes with their corresponding set of answer labels, the goal is to learn a function G that maps these inputs to answers about the unseen scenarios. So this paper mainly focuses on the three types of neural network structure. The first one is MLP. So MLP are the simplest neural networks. It consists of fully connected layers. They work well with tasks involve individual objects, but they often struggle with the relationship, struggle with the tasks that need to deal with the relationships between different objects. The second architecture is deep sets. It is designed for the tasks, while the input is a set of objects, and the and the and in the in the architecture of the deep sets indicates that this neural network are permutation invariant. So their architecture in this formula, their architecture involves two MLPs. The first one will extract the features for each object, and the second will aggregate the results into a single output. And this architecture always perform good at tasks like computing the summary statistics, but it will fail to the model relationships between pairs or groups of objects. The last architecture is graph neural networks. So graph neural network are specifically designed for relational reasoning. So they model the objects as nodes in the graph, and the relationships between them as the edges. So the information is propagated iteratively across the graph. And this architecture will allow graph neural network to learn the relational patterns. And also, this will make them particularly effective for tasks like solving the pairwise reasoning problems. Okay, let me summarize their capabilities. For MLP, they are fast and simple, but they always limited in the tasks of dealing in which including the relational reasoning. And for deep sets, they are good for aggregation tasks, but they lack some relational modeling. For graph neural networks, they they are most flexible and powerful for the relational tasks, but they always require a higher computation cost. In fact, many neural networks can represent algorithms. For example, there is a theory about deep sets. For deep sets, it can universally represent the permutation invariant set functions. Here are some simple examples. When we computing the maximum value or the sum of a set of numbers, which involves no particular input order, these tasks are the permutation invariant task. So the architecture of deep sets is well aligned with these tasks, since aggregation over the entire sets is required. So for proposition 3.1, It states that any continuous function f defined over a set S can be approximately arbitrarily closed by a graph neural network. And the results in this proposition 3.1 highlights emphasize the universal approximation ability of graph neural networks for some permutation invariant functions. Then for proposition 302, it states that for every graph neural network N, there exists an MLP that can represent all functions that N can represent. So this proposition indicates that graph neural network does not have inherently greater representation power than MLPs, but instead their advantage lies in their structure, which aligns with many reasoning tasks. Well, another thing is, although MLP can theoretically replicate the GNNs functionally, but it would need to explicitly learn a graph structure and pairwise relationships, and this will make the learning process more difficult. In fact, the neural network structure, the structure of neural network are the computational structures on the function it computes. So this corresponds to an algorithm that can prescribe how the network combines the computational from each modules. So here is an example as this figure shows. It compares the iterative reasoning process of a graph neural network and the algorithm, Bellman-Ford algorithm for shortest path. We can see here the last step in Bellman-Ford algorithm, it is similar to the reasoning process in the graph neural network. Because the information is iteratively aggregated and propagated. And also, in this graph neural network, it does not need to explicitly learn the outside for loops because the iterative reasoning process is built in the graph neural network structure. Therefore, we can see this is a very good example of the algorithm alignment. Then we have the following observation. A neural network which better aligns with the correct reasoning process can more easily learn a reasoning task than a neural network that does not align well. Okay, then we move forward to the algorithm alignment. So before introducing the formal definition, I will first introduce the pack learning framework because the algorithm alignment is built on this framework. So let's look at the definition 3.3. The goal of a learning algorithm is usually to approximate an unknown function as closely as possible using a set of training examples. So in here, we'll let y equals to gxi, meaning that the output labels are generated by the underlying true function g. So let f be the function learned by the learning algorithm A. And based on this, and also it will obtained based on the training samples. So the function gx is said to be m epsilon delta learnable with the algorithm A if the learned function fx satisfies the following conditions. So the sample complexity here, Ca, is the minimum number of the samples M required that are required for the algorithm A to learn JX within the given error and the failure probability here, delta. So from this definition, it formalizes what is means for a learning algorithm to generalize well. So in the context of this paper, this PAC framework provides the foundation for analyzing how the algorithm alignment of a neural network within a reasoning task will affect its sample complexity. Well, in this paper, also called hard to learn or easy to learn. For example, for a graph neural network, we can the graph neural network aligns well with the dynamic programming tasks. If it happens, then the graph neural network is expected to have lower sample complexity because it can efficiently approximate the GX. Then we are ready for the formal definition of algorithm alignment. So this definition explains when a neural network is well aligned with a reasoning function and why this alignment matters for learning efficiency. So here, suppose G is a reasoning function. For example, the shortest path computation, and we let N be the neural network with N module. And for example, the layers or the components in the network structure. So each module Ni here can be replaced by a corresponding function Fi that simulates some part of G, the target function G. So if this replacement allows N to simulate G, we say that the network is aligned with G. So when this alignment occurs, it needs to satisfy the following two conditions. So the first condition is the module F1, use the module functions F1 to Fn, we need to make sure that it will generate the G, the target function G. And the second one is the learning algorithm AI for each module have a bounded sample complexity such that the total complexity N multiply Ca is less than or equal to the M. So essentially, this means that the network can simulate the reasoning function efficiently with minimal data requirements. So this definition provides a theoretical basis for understanding why some neural network architectures generalize better than others. When a network is well aligned with the tasks, its structure naturally supports efficient learning. Then we have the main results in this paper. So this theorem provides a formal explanation of why algorithm alignment is crucial for reducing the sample complexity in neural networks. And additionally, it highlights how neural networks that align well with reasoning function of a task can be learned more efficiently. So here, let's look into this theorem. We are given a data set, and the network N consists of N small modules, sequential modules, and it should be algorithmically aligns with G via using some function F1 to Fn. So the goal here is to determine the condition under which G is M O epsilon O delta learnable by N. So this theorem makes three important assumptions about the learning process. The first one is the algorithm stability. So the learning algorithm for the network modules Ni must produce output F that can approximate G for G with a bounded error here. It has a constant L0. And the second one is sequential learning. So that means the network is trained sequentially. So each module Ni uses the outputs of the previous module as its input. And we should ensure that the reasoning steps are learned in the correct order. The last one is the Lipschitz. So that means the learned function are Lipschitz continuous, meaning that the small changes in the input will lead to a proportional small change in the output. Therefore, so under these assumptions, this theorem states that if the network N is well aligned with G, then G can be learned with sample complexity M, which that is proportional to epsilon and delta, which is defined before. So this means a better alignment directly leads to a more efficient learning. Okay, so to illustrate the algorithm alignments, the paper provides several examples of reasoning tasks. The first task is summary statistics. It is evaluate whether models can compute aggregate statistics like sums, maxima, and minima efficiently. One example is what is the maximum value difference? What is the maximum value difference among a set of objects? So, in this paper, for different tasks for the three considered architectures, the paper always make a prediction first. In DeepSet, the structure indicates that they will successfully compute the maximum minimum due to the alignment with the aggregation process. And for MLP, they may fail because they require learning the complex loops for compute the maximum minimum operations because they are talking about the relationship. The paper also provided the empirical study on this task to validate their theoretical findings. So here is the result. We can see that the deep sets outperform the MLP. So, in here, we know there is a sorted MLP. So the reasoning algorithm for a sorted MLP will reduce to a simple subtraction. So the performance become much better than the MLP. So GNN, here we can see that graph neural networks also have high test accuracies. This is because the summary statistics are a special case of the next task I will talk about later, relational argmax. Okay, so from the results, we can see the results validates the theoretical findings. Then we move to the next task, relational argmax. So it is about evaluate models on tasks that requiring pairwise comparisons and identify the specific relationships. So here are some predictions about the considered architectures. So for one iteration graph neural network, it will sum over all pairs of objects. Then it will compute our target. So it will be success because the architecture inside the graph neural network. So for deep sets, it will fail based on the theorem. So because it has to learn a complex for loops and it has a bad algorithm alignment. So a very specific given a specific example is furthest pair. So it is the target of this task is to find what is the color of the furthest pair of the objects. So here is the example experimental result. So as their prediction, the deep set has only 21% accuracy, while GN have more than 90% accuracy. Okay. The third task is dynamic programming. So that dynamic programming will recursively breaks down a problem into some simple subproblems. It always have the following form. Here the answer Ki is the solution to the subproblems indexed by the iteration K and state I. And then the DP update is an task-specific update function that will compute the answer Ki from the previous answer K minus 1, answer K minus 1J. So the theorem from the previous theorem, it suggests that a graph neural network with enough iterations can efficiently learn any dynamic programming algorithm with a simple DP update function here. For example, some summation, minimum maximization. So one example used in this paper is monster trainer. It is a variation of shortest path task. And to solve this problem, this paper also used Bellman-Ford algorithm. So the figure here shows the empirical results. So we can see that the empirical results confirms the prediction. A neural network can sample efficiently learn a task if it is aligned with the correct algorithm. So here, another observation is graph neural networks does not need as many as near iterations as Bellman-Ford. So, for example, in the paper, it states that for Bellman-Ford algorithm, it needs 7 iterations, but for graph neural networks, it only needs 4 iterations. And within the 4 iterations, it will have the most identical test accuracy as a Bellman-Ford algorithm with 7 iterations. So this can also be explained through the algorithm alignment. So because the graph neural network aligns with an optimized version of Bellman-Ford algorithm. And this is the last task. So for some reasoning tasks, such as NP-hard problems, it will go beyond the dynamic programming. For example, the subset sum. For this task, the input is a set of numbers, and the goal is to determine if there exists a subset that their sums is equal to 0. So graph neural networks fail on NP-hard tasks because they are lack of alignment with exhaustive search process. But then to address this issue, this paper introduced the neuron exhaustive search architecture. It is a neural network that will enumerate all subsets and then process them using an LSTM and MLP neural network architecture. So from the results, we can see that NES achieve high accuracy. Here we can see it up to 98%. Well, for other models like GNs achieve only achieve near 70% accuracy. So to summarize, in this work, it introduces algorithm alignment as a framework to analyze the relationship between the reasoning tasks and network structures. And it demonstrates that the task-specific architectures, such as graph neural network for relational reasoning and NES for NP-hard problems, will significantly outperform other genetic designs. So this study also provide both theoretical and practical insights for designing neural networks that can better suited for complex reasoning tasks. Okay, that is all for my presentation. Thank you for watching.